Okay. Well, welcome everyone to today's BNP webinar. Our speaker today is David Dahl. David is a professor in the Department of Statistics at BYU. His research interests focus on Bayesian nonparametrics, model-based clustering, random partition models, protein structure prediction, bioinformatics, and statistical computing. The title of his talk today is Shrinking a Partition Distribution Towards a Baseline Partition, with applications to dependent partitions. As always, you can ask clarification questions during the presentation, and we ask you to hold all non-clarification questions until the end of the presentation. You can also use the chat to ask your questions. This time we have Richard Ward, one of the co-authors of this work, who will be available to answer any questions directly in the chat. David, thank you for accepting this invitation, and without further ado, please join me in welcoming David.
All right, thank you very much, Felipe, for the introduction. Thanks, Subhashish, for the invitation to speak, and Alessandra also as the program chair for the BNP section. It's a pleasure to be here, and I'm super excited to talk about this work. I want to give a shout out to my co-authors, Richard War, who, as Felipe mentioned, is on the chat and can answer any questions on the chat throughout the talk. And also Tom Jensen, a student at BYU who is now working for Berry Consultants. So what we're going to be trying to do is talk about a way in which we can modify a partition distribution to use a best guess partition that is the baseline partition. Now, to motivate the talk, I want to give a little motivating example where we're going to be interested in looking at a regression where the left-hand side variable is the log of the average hourly earnings, and we want to regress that response on a bunch of covariates, but in particular we're interested in some education dummy covariates to see the degree to which a bachelor's degree increases your log average hourly earnings relative to a high school degree, or say how much an advanced degree would increase your wages. Now we have available to us data from the Bureau of Labor Statistics, which every March collects detailed wage information from about 4,000 participants. And we have data from 2007 to 2020. Now we can just take all of that data from 2007 to 2020, all 14 years, and run that wage regression, and then estimate the coefficients of interest associated with the education variables. But we might recognize that the Bureau of Labor Statistics breaks up the United States into 4 different regions, presumably because the labor markets are different across the United States. And so maybe the Western states are more similar in terms of the labor markets than, say, the Northeast or the South, for example. So we could certainly do an analysis for each of the 4 regions separately using all data from 2007 to 2020. And that actually leads to a better LPML value, log pseudo marginal likelihood value, where bigger is better. And in this case, that means less negative. And so doing an analysis region by region is better than putting the data all together. But why stop at the region level? We could further divide the United States into what are called divisions. There are 9 different divisions of the United States, and we can actually get an improved LPML value by breaking the data analysis up into divisions. Well, again, why stop there? Why don't we do an analysis specific to each individual state? And so that's fine, and we can do that because we have a lot of data from 2007 to 2020. And so this singleton or state-by-state analysis actually leads to the best LPML value. But doing this analysis requires us to aggregate the data from all the years 2007 to 2020. But what if we wanted to do some year-specific estimation? Now, if we still follow the state-by-state strategy, the singleton strategy, that would involve state-by-year specific estimates. And so there's something like 714 regression coefficients in that context. I'm sorry, 714 regression coefficient vectors to estimate in that context. And so the data is going to be too sparse to support such a flexible analysis. there are about 80 observations per state year combination. And in fact, for California, the most populous state, that's going to work fine. We'll have more than 80 observations, and we'll be able to estimate that just fine. But for small states, we have very limited data, and we'll have a very hard time estimating state year specific estimates. So perhaps we can get state year specific estimates if we add some structure to the problem. That is, if we can borrow strength across the states and across the years using random partition models. Okay, so let's talk about random partition models, and in particular, some notation for partitions. So a partition pi is a set of subsets of the integers 1 to n, such that the subsets are non-empty, mutually exclusive, and exhaustive. Now, the number of subsets in a partition pi can range from 1 to n. If we put all the data together, that's then going to be just one subset. Or if we do an analysis individually for each state, that's going to lead to n subsets. Now, we refer to subsets and clusters interchangeably. And likewise, we might use partition notation, but we could also represent a partition in terms of cluster labels. Label pi 1 up to pi n, where pi I equals j if and only if I is an element of subset Sj. So we have a very big space of partitions of n items. It grows according to the Bell number, and we're talking today about probability distributions over this very large discrete space. Now, our favorite partition distribution is probably the Chinese restaurant process, or maybe it's two-parameter extension. And that is the tried and true random partition model. And it has a rich connection to Bayesian non-parametrics, where when we integrate out the random measure, say, from the Dirichlet process, we get back the Chinese restaurant process. Now, there's been work where we would want to use covariates to be able to influence the partition distribution. We might have, for example, a covariate vector, and maybe two items that have very similar covariates should be more likely to be clustered together than items that have very different covariates. There's a paper by Bly and Fraser that looked at that, the distance-dependent Chinese restaurant process. Peter Mueller, Fernando Quintana, and Gary Rosner have their PPMX method, which is quite popular. Park and Dunson have also worked in this area. And then I have a paper with some co-authors, Jerry Tsai and Ryan Day, where we do the Ewens-Pittman attraction distribution, which then lets pairwise distances influence the partition distribution. And those pairwise distances may be obtained from covariates or any other distance metric you might have. But today we're talking about something different. We're talking about what if we had prior information about the partition itself? That is, how can we include a prior guess of a partition for a partition distribution for an unknown partition? That is, we want to have a random partition distribution that's influenced by, not covariates, but influenced by a prior guess itself. Now, there are two pioneering works in this area. The centered partition process of Sally Paganin, Amy Herring, Andy Olshan, and David Dunson. Their CPP method was published in Bayesian analysis earlier this year. It was in a paper with a discussion, 2 invited discussions and lots of contributor discussions, a really nice paper that we are excited about. There's another paper, the location scale partition distribution, was proposed by Adam Smith and Greg Allenby, and they also propose a partition distribution that's influenced by a best guess partition. These two papers seem to be simultaneous work, and they both really lay out this really nice area. What we're doing today is taking the pioneering work of these two papers, the CPP and the LSP, and addressing some of the missing features to provide what we think is a really nice partition distribution influenced by a best guess partition. And so we're going to be going through point by point all of these different properties that our shrinkage partition distribution has that are present in some of the CPP and the LSP, but not all. But before we go through these individual properties, though, I should introduce exactly what we're proposing for this CP and also contrast that with the CPP and the LSP. Okay. All right, so first of all, our shrinkage partition distribution. Okay, the probability mass for our shrinkage partition distribution is a distribution for a partition that is influenced by a baseline partition mu and a shrinkage vector and also a baseline partition distribution. So this could be, for example, the Chinese restaurant process, or it could be the distance-dependent Chinese restaurant process, or it could be the PPMX method, or the Ewan's Pittman attraction distribution. The baseline partition distribution can be anything that you would like to use. And what we do then is we take that baseline partition distribution and shrink it towards the baseline partition. And the degree to which we shrink is given by the shrinkage vector omega. Now, how we actually do that then is we take the product as I goes from 1 to n of these individual allocation probabilities, which are given by the baseline allocation probability, modified by the degree to which the allocation is compatible with the baseline partition. Now, I don't want to scare you with the details here. We're going to see an example that this is actually a very simple quantity to compute. But do notice that we are taking the product as I goes from 1 to n. And as such, then our partition distribution will be dependent on the order of the data. We're using what's called the natural order, 1, 2, up to n. And of course, we don't want to have our data analysis depend upon the order in which we happen to observe the data. And so what we want to do is introduce a permutation parameter, sigma. And the permutation parameter, sigma, is something that allows us to then have our data analysis be invariant to the data order. The permutation sigma tells us the order in which we allocate items. We don't know what that value is, and so we go ahead and put a uniform prior on sigma. It's very simple in MCMC to update the value of sigma, and then we can integrate it away using Monte Carlo integration. And so once we introduce the sigma, the notation gets a little bit more complicated. So we now have double subscripts. We have a sigma, and then there's some double subscripts now. But the point is that we have these item-specific shrinkage values, which allow us to reward those allocations which are compatible with the baseline partition. Well, let's see how simple this really can be by looking at a little toy example where suppose that we have n equals 7 items and our baseline partition says that 1, 3, 6, and 7 are together, 5 is by itself, and 2 and 4 are together. Our random permutation, suppose, is allocating first item 4, then item 2, then 7, all the way up until the last item gets allocated, and that's item 5. We also have then item-specific shrinkages, omega 1 to omega 7. So first we allocate item 4. Well, 4 goes to a cluster by itself, obviously, it has to go somewhere. 2, let's suppose, goes with 4, which is something we would expect because that is what our baseline partition distribution says. And we keep on allocating according to the allocation rule given by the shrinkage partition distribution. Let's slow down, though, as we think about the allocation of item 3, just to look at a little more deeper. Item 3 could either go in the first cluster, the second cluster, the third cluster, or it could go to a new cluster. And so we want to look at then the probability that it goes to each one of these different clusters. Okay, well, the probability is going to be proportional to some probability from the baseline distribution, where we have then a reward to the extent to which allocating item 3 to a particular cluster is compatible with the baseline partition. Now, notice that in the baseline partition, 3 is with 1, 6, and 7. And so we don't want to reward 3 going with 2 and 4. And so we have 0 here times the omega, which is then 0. E to the power of 0 is just 1. And so those things, that drops away, as does allocating 3 to a singleton cluster drops away. But notice that...
David,
yes.
Excuse me, but omega is positive?
Omega is positive, yes.
Okay, thank you.
So you can see that if omega is equal to 0, we get back just the baseline partition distribution. And to the extent omega is big, we're encouraging more fidelity to the baseline partition. Thanks, good question. All right, so allocating item 3 to this cluster is certainly compatible with the baseline partition information, but also allocating item 3 to this cluster is also compatible because, for example, 6 is indeed with 3. And so we need to split up the shrinkage omega 3, 2/3 goes to here and 1/3 goes to there. And so we're encouraging those things that are compatible. So suppose that we consider various different baseline partition distributions. The baseline partition distribution could be, for example, the Ewens-Pittman attraction distribution that's based on pairwise distances, or it could be the Jensen-Liu partition distribution. This was proposed in a JASA paper by Shane Jensen and Liu, in which the allocation was uniform to all existing clusters, and then there was a concentration parameter that governed the distribution or allocation to a new cluster. We could also have it be the uniform partition distribution or the Chinese restaurant process. If it were the Chinese restaurant process, it would just be 2, because there are 2 existing items here, or 2 here and 1 in alpha. So it's a very simple calculation to do. And the point is that we've defined this probability up to a normalizing constant, but we could very easily evaluate each of these 4 things and normalize to get then the exact probability of allocating to each of these 4 different configurations. Let's talk about 5. Notice that 5 in the baseline wants to be by itself, and so that's the one that we end up rewarding. And so depending on how big omega 5 is, the reward could be 0 if omega 5 is 0, but the reward could be substantially bigger for larger omega 5. The point is that we end up having some partition which is allocated according to these allocation probabilities, and for which we can then compute the allocation probabilities and take the product of them, and then we have the probability mass function evaluated for that particular partition. Now let's compare that with the location scale partition distribution of Smith and Allenby. They also allocate sequentially, item 1 first, and then item 2, all the way up to item n. So they use the natural permutation, and their allocation rule is somewhat different. But nonetheless, it involves then a sequential allocation. They have a baseline partition, and they also have a shrinkage parameter omega. This shrinkage parameter omega, though, is not specific to individual items, but is rather a global shrinkage parameter. And in fact, I say shrinkage parameter, but in fact, as they first proposed their distribution, they called the location what I'm calling the baseline partition. And they also have a scale parameter, and we're using the inverse of that to be our shrinkage parameter. So we've taken the liberty to reparameterize their distribution. It's the same distribution, just with a different parameterization, so that we could do better comparisons. All right. Well, let's talk about the CPP from Paganin et al. Now, the beauty and the Achilles heel, I think, of the CPP is the following. The probability mass function for a given partition pi in the CPP is proportional to the probability mass function evaluated at that given partition pi, modified by a penalty as indicated by the distance that pi is from the baseline partition. That penalty is governed by this omega, the shrinkage parameter, and the distance is measured by, say, the binder loss function, or as they recommend in their paper, the variation of information loss. The point is that when pi is the same as omega, the distance is 0, so there's no penalty relative to the baseline. But to the extent that the distance of pi to mu is large, that means there's substantial penalty, and we're then trying to penalize the probability associated with a particular partition that is far away from the baseline partition. But notice that they've only defined the probability mass function up to a normalizing constant, and that's going to then make it tricky to make inference on the omega shrinkage parameter. Okay, let's take a look at these properties one by one. So one thing you saw is in the formulation of the shrinkage partition distribution and in the CPP, we could accommodate any baseline partition distribution. Now that's not the case with the LSP. So recall when the omega parameter is equal to 0, we recover the baseline partition for both the shrinkage partition distribution and the CPP. So great, when the shrinkage parameter is 0, we recover back the baseline partition distribution. To the extent that the shrinkage is bigger, we then are being pulled towards the baseline partition. Now the LSP, however, doesn't have flexibility in specifying the baseline partition distribution. So if we set omega to 0, what is the baseline partition? Well, when it's 0, this all falls out, and we end up having just this as the allocation rule. Now, as you study that, you see, oh, okay, the allocation to an existing cluster or to a new cluster is uniform. Well, that's exactly what the Jensen-Liu does, except the Jensen-Liu is a little more general in the sense that there's a concentration parameter alpha right here that allows you to govern the distribution of the number of clusters. So we could generalize the LSP just a little bit by introducing this alpha parameter, but still, nonetheless, baked into the LSP is this particular allocation rule, which is the Jensen-Liu partition distribution. Okay. In the interest of time, I don't think I'll talk too much about the CPP's problem in scaling in the sample size n, but I think it's just worth noting quickly that because they don't have a tractable normalizing constant, they have to deal with some messy combinatorics, and they have a method by which they can fix the value of omega through some cross-validation when n equals 26, which was their example size for their data analysis. And they readily acknowledge that it will not scale in the sample size n. But yet we can still follow their general framework to be able to fix the value of omega for larger n, as we suggested in our discussion of their paper in the Bayesian analysis paper. So that's nice, but nonetheless, the omega is still fixed. And not only is omega fixed, but any parameters influencing the baseline distribution, say, for example, the concentration parameter or the mass parameter of the Chinese restaurant process, that also needs to be fixed. Well, recall that the shrinkage partition distribution introduced a permutation to govern the order in which we allocate items into the clustering, and we put a uniform prior on that so we could then randomize over the order. That then makes our data analysis invariant to the order in which we allocate items. The CPP is also invariant to the order in which the data is presented, but the LSP uses inherently, explicitly, the natural ordering, first allocating the first item, then the second item, then the third, and then the nth item, which leads to kind of some puzzling properties. Consider a case where n equals 4, and we have as our baseline partition saying that 1, 2, and 4 are together, but then 3 is by itself. We could look at the implied pairwise probability that items are clustered together a priori. The probability under the LSP that 1 and 2 are together is 0.67, but the probability 1 and 4 are together is 0.51. And that's a little bit odd because in our baseline partition, we said that we thought 1, 2, and 4 were together. And it seems odd that the probability 1 and 2 are together is larger than the probability 1 and 4 are together. Whereas in our shrinkage partition distribution, because we're using a random permutation, we have nice intuitive pairwise probabilities that say 1 and 2 are together and 1 and 4 are together being the same. The CPP also likewise is invariant to the order of the data. Now what we could do is we could take the LSP and we could introduce a random permutation to then solve the problem of them being dependent on the order, and then we can solve the problem just by taking the ideas from the shrinkage partition distribution, that is a random partition, and apply that to the LSP. So we'll put a little check mark there. Our extension to the LSP would allow for a random permutation. Now, all three of the methods have the next property, which I want to discuss now, and that's a consistency property. So suppose that we have n equals 5, and that our baseline partition says that 1, 2, and 3 are together, and 4 and 5 are together. Now, with n equals 5, there are 52 possible partitions of those 5 items, and we can compute the probability of each of those 52 partitions. We could order those 52 partitions, and we could then stack the probabilities, as we've done here. Now, when the shrinkage parameter is equal to 0, we just get back the baseline partition distribution. And as we increase the omega, we are favoring then partitions that are compatible with the baseline partition. And eventually, as omega goes off to infinity, all probability mass collapses to the baseline partition. And this is a plot from the shrinkage partition distribution, but similar plots could be done and look very similar for the CPP and the LSP. Now remember that our shrinkage partition distribution has item-specific clusters, or I'm sorry, item-specific shrinkages, or in fact, we could do cluster-specific shrinkages if we want. And that's not something that the CPP and the LSP can do because they have a single univariate global shrinkage parameter. And so you have to then shrink uniformly to the baseline partition. But we think that in practice, actually, there may be cases where you might think that we want to shrink more strongly, say, in the Western United States and less strongly in the South. Or maybe we've got big states like California, Texas, and Florida, and New York, for which we have sufficient data that we don't want to try to encourage them to cluster with other people in their region. Maybe we'll let them float according to what the baseline partition distribution would want to do. Well, the fact that we have cluster-specific shrinkages then allows us to have that flexibility. And what that does then is leads to these really interesting plots. Again, suppose that our baseline partition is the same as before, 1, 2, and 3 are together, and 4 and 5 are together. But in fact, we don't really believe that 4 and 5 are together because we're going to have the item-specific shrinkages for 4 and 5 be fixed at 0. And we want to see now what happens to the probabilities as omega goes off to infinity, where omega is only affecting the first 3 items 1, 2, and 3. And we see that then items 1, 2, and 3 are kind of fused together as omega gets big. But 4 and 5 are free to float because we have a shrinkage of 0 for items 4 and 5. And so then the probability of all probability for a partition reduces down to partitions in the set of those that are compatible with the baseline partition and compatible with our 0 shrinkages. Now we can take the LSP and we can likewise introduce item-specific or cluster-specific shrinkages as an extension, much like we've done with the shrinkage partition distribution. So there is a way to do item-specific shrinkages with the LSP with our modification. Let's talk now about inference on hyperparameters. Now, the probability mass function for the shrinkage partition distribution is just a product over these individual allocation probabilities. And of course, we can compute the normalizing constant of each of these individual allocation probabilities because we're only allocating to the existing clusters or to a new cluster, and we can very easily then compute the normalizing constant and then compute the probability altogether. That's not the case for the centered partition process, the CPP. The combinatorics are such that getting the normalizing constant is very tricky and will be impossible as the sample size n increases. And so what to do? Well, we can't put prior distribution on hyperparameters. We can't put a prior distribution on the shrinkage parameter, for example. And that then precludes us using the CPP for modeling dependent partitions, which we'll talk about at the end of the talk. The LSP, however, can make inference on hyperparameters because they indeed also have a known normalizing constant. I will say, though, in the paper, in their examples, they seem to always use a fixed value for the shrinkage parameter, but we think that's not what you'd like to do, we are advocating for putting a prior distribution on the shrinkage parameter. And I want to explain why that is now. So when the shrinkage is equal to 0, then the shrinkage partition distribution is the same as the baseline partition distribution. And we could compute the distribution of distances of partitions from the shrinkage partition distribution with shrinkage at 0 to the baseline partition mu. And this is the probability mass function of the distribution of different distances as measured by binder loss of draws from the shrinkage partition distribution with shrinkage at 0 from the baseline partition. Now, as we increase the shrinkage, we expect there to be smaller distance from the baseline. And in fact, that's what happens. As we increase the shrinkage, we pull the distribution towards the baseline partition. And so that's why we call our method the shrinkage partition distribution, because we're shrinking the partition distribution towards the baseline. And indeed, as we increase the shrinkage, we get more pulling towards the baseline partition, closer to a distance of 0. But notice that we have to get the shrinkage to be quite large before we get things quite close to 0, quite close to the baseline. And in fact, in so doing, we also reduce the variability. And so everything's close now. And when shrinkage is small, everything's reasonably far away. There's nothing right there at 0, which seems a little bit odd to us. But we recognize that if you put a uniform prior on the shrinkage, then the distribution of binder loss from the baseline can be much more spread out. We could have some partitions that are right there, right at the baseline, but we can also have substantial movement away from that for larger values of the shrinkage. That is when we use a uniform shrinkage prior. The same could be said for the LSP. That is, we would advocate when using the LSP that you also consider using a random shrinkage as opposed to fixing it as they do in their examples. Finally, we're providing an R package that implements our shrinkage partition distribution. And in fact, we also implement the CPP and the LSP in our package that you could then use for comparisons. Okay, let's look at a simulation study to see how well these methods actually work. Okay, so what's the simulation design? So we want to consider comparing the shrinkage partition distribution, the LSP, and the CPP, where some baseline information is correct, but not perfect and maybe mistaken in some places. So our baseline partition is going to be 4 clusters of 10 items each. And the LSP and the CPP have a global univariate shrinkage, omega. And our shrinkage partition distribution, yes, can have a global univariate shrinkage, but we can also have cluster-specific shrinkages. And in this case, we're going to have the shrinkage for cluster 4 be 0, saying that we don't really want to try to encourage items that we put in cluster 4 to be together, per se. But we're going to have then a uniform prior on the other 3 shrinkages for the 3 clusters 1, 2, and 3. And what we need to do, though, is we want to make sure we're doing a fair apples-to-apples comparison. And so we need to have it be such that the shrinkage values are fair, so they're shrinking about the same amount towards the baseline distribution. And the calibration that we use is based on some pairwise probabilities, where we want the pairwise probability of items that we said were in cluster 4, or cluster 1 is about 0.8. Those that we said were in cluster 2, the pairwise probability is about 0.8 on average, and those that are in cluster 3 is about 0.8 on average. And so we calibrate in that way based on these pairwise probabilities to make it then fair comparisons. Okay, now the nice thing about this particular formulation is that we have this calibration done once, and now we can repeatedly generate data where the truth is what's changing. So the true partition is going to be just a copy of the baseline partition, except items in clusters 1 and 4 are going to be reallocated uniformly and independently among 1, 2, 3, and 4. As such, then, the clustering information in 1 and 4 from the baseline is really wrong, except we're going to be okay in the case of cluster-specific shrinkages where we set the shrinkage for item 4 to 0, but still, nonetheless, we have misspecified the cluster 1. The data is going to be generated from a normal distribution, and the model parameters are also sampled from a standard normal distribution. And the game is going to be to estimate or recover these model parameters. Now, as our reference, we're going to see how well the Chinese restaurant process does in estimating these model parameters. We're going to compute the mean square error and find the mean square error under the CRP is 0.101. And then these R methods that we're comparing here today then are an improvement over the CRP. And the degree to which we improve is indicated here. The shrinkage partition distribution does better than does the LSP, and substantially better than does the CPP. Now, there are lots of choices to make in the particular distributions we're using. You might say, well, this is not a fair comparison because the LSP has a built-in baked shrinkage, has a built-in baked baseline distribution being the Jensen-Liu, but yet here for the shrinkage partition and the CPP, we're using the Chinese restaurant process. Well, we could certainly then redo our methods using the Jensen-Liu partition distribution as the baseline distribution. And that's a more fair comparison. But notice that we're using the VI distance for the CPP, but we could also, and that's what they recommend in their paper, we could also, however, use binder, and binder actually leads to an improvement. In fact, if we use binder loss with the CRP as the baseline distribution, the CPP then performs about as well as does the LSP. Now, not exactly fair because in the LSP, remember, we have a fixed mass parameter at 1, although we can generalize it to have then using the Jensen-Liu idea, we could then use concentration parameter alpha and let that float, let a prior distribution be put on that. Likewise, we could modify the LSP to have then a random permutation. And in fact, we could also modify the LSP to have a random shrinkage. Well, when we do that, we get a slight improvement for the LSP. But you still might say, well, that's not a fair comparison because, hey, you're using cluster-specific shrinkages, whereas the LSP and the CPP can't use cluster-specific shrinkages. Well, that's kind of the point, is that we're have a scenario where having cluster-specific shrinkages is a real benefit to us, and the LSP and the CPP can't have cluster-specific shrinkages. We looked at the prior and posterior distribution for the shrinkages for cluster 1 and for cluster 2. Now remember that cluster 2 was good clustering information, and in fact, our prior was uniform on the shrinkage, and we're able to see that in the posterior, we have desires to have big values of shrinkage, because that is indeed true in the data simulation, in the data generation mechanism. Now in cluster 1, though, we misspecified. We, in fact, the cluster 1 was one in which the prior information we had was bad, and the model is able to pick that up and able to move the shrinkages towards 0 relative to the uniform that we originally had. So I think that's a really nice property. But then you could still say, well, you know what, though, that's not fair. You're using cluster-specific shrinkages. It's not fair. LSP and CPP can't do that. And so, yes, we could make this shrinkage partition distribution have a global shrinkage. And in so doing, we lose a little bit of performance, but yet we still are at least as good as the LSP and perhaps substantially better. This also illustrates the idea that it's nice to be able to have the ability to specify the baseline partition distribution and not have it be fixed at the the Jensen-Liu partition distribution as the LSP requires you to do. Okay, let's move back to the application to dependent random partitions. So our framework is going to allow us to model a time-dependent collection of partitions, pi1, pi2, up to pi t. So for example, in a time series context, we might have that at the first time point, we have a partition which is distributed according to some random partition distribution. And then given that random partition pi1, that becomes the baseline partition for the distribution for the next partition at the next time point. And so our shrinkage partition distribution allows us to have that dependence relationship, and the extent to which pi I and pi I minus 1 are similar to each other is going to depend on the shrinkage parameter omega. If omega goes off to infinity, pi I minus 1 and pi I will be exactly the same. And to the extent that omega is 0, then pi I and pi I minus 1 will be independent and just drawn from the baseline partition distribution. Now, what we use for our original random partition for the first time point could be, for example, the CRP, or it could be any other partition distribution you want to use. And in fact, you could use our shrinkage partition distribution, where you had some guess as to the partition mu. Now, an obvious model in which we want to compare would be a paper that's coming out in JCGS by Garrett Page, Fernando Quintana, and myself, where we have a particular formulation to model a dependent sequence of random partitions using some latent variables and pegging some values and letting some other values float. The degree to which we have pegging induces correlation. That's a really nice approach that is a very natural competitor to what I'm proposing here. Now, going back to the regression analysis for the return to education, recall that we had these results here. When we combined years 2007 to 2020, we found that an analysis for everybody all together was not as good as breaking things up into regions, divisions, or in fact, even doing individual state-specific estimation. And that worked well because we had a lot of data across all 14 years. But if we were to do the analysis year by year, and then summing up over all the years, we find almost the exact opposite is true. Now, putting everybody together leads to better values than doing a singleton analysis, a state-by-state analysis. And in fact, if we were to use the CRP, we could even do better than putting everybody all together. And in fact, if we were to use our regions information from the Census Bureau, we could even do better using our shrinkage partition distribution. But this is still one analysis year by year, and we have not yet implemented the time-dependent partitions like we have here. And so that is still a work in progress. And we expect, though, that the clustering of the states in 2007 should be related to the clustering of states in 2008 and should be related to the states in 2009. And so we want to take advantage of that rather than treating the partition process as if it was completely separate analyses year after year, as if Alabama completely changes from year to year in their labor market, which we don't think would be the case. Likewise, we can consider hierarchically dependent partitions. So we want to think about a collection of partitions. We want to model hierarchically. So we might have partition pi 1, pi 2, up to pi k. And so for each data analysis, we have a partition pi I. Or perhaps maybe we have a regression analysis where we have a group of covariates that we want to partition, and another group of covariates that we want to also partition, but we don't want to constrain the partition for the first group of covariates to be the same as the partition for the second group of covariates. But yet we might like to have it be that there's some sharing of information in these two different partitionings. Or maybe we're partitioning covariates, but we're also partitioning a variance. And maybe the partitioning of the variance could have something to say or help us partition regression coefficients. Yet we don't want to force them to be fused together. Well, how can we do this in a Bayesian model? We want to do basically hierarchical clustering then for partitions. Well, we can do that quite simply with a formulation like this. Maybe we have a global partition mu, which is drawn from some partition distribution, say the CRP, and then that becomes the baseline partition from which these individual partitions are drawn, and the extent to which the omega, or excuse me, the extent to which the partition pi looks like the baseline partition mu is governed by our omega parameter. If the omega is equal to 0, we have a bunch of independent partitions all drawn from the baseline partition. And to the extent that omega goes off to infinity, all of the partitions, pi I, will exactly replicate the baseline partition mu. So by way of conclusion then, we have proposed then the shrinkage partition distribution, which takes a baseline partition distribution and shrinks it towards a baseline partition, a best guess. We're really excited about the fact that we have item-specific or cluster-specific shrinkages, which we think really brings a lot to the table, because we think it's very natural to think that we might have a prior guess as to the clustering of some things, but not as much information about the clustering of other things. And it's natural to want to then be able to have differential shrinkage information brought into the analysis, as opposed to having us have to have a global shrinkage parameter. Our approach has a tractable normalizing constant, which then permits us to do posterior inference on hyperparameters, and also then is the key to be able to do dependent modeling of partitions, either in time or in a Harkle fashion. And if you're interested in trying these things out, keep an eye out for a pumpkin package, which we have developed and are preparing for release to CRAN when we submit the paper. With that then, thank you very much for your attention. It's been a pleasure to present at the seminar series. Thanks.
Okay, so let's thank David for his presentation. We have time for questions, comments. So if you have any, please turn on your mic and go ahead, or you can also raise your hand.
I mean, I have a couple of questions, but I can wait for somebody else to make questions before myself. Well, Felipe, so if there is nobody else.
Nobody else, so.
Okay, so can I ask my question, David? Well,
yes,
thank
please.
you very much. I really enjoyed the talk and the model. Really, really interesting. And I was wondering if the prior that you put on your omega I parameters, you said it's a uniform. Why a uniform? Because it's easier from the computational point of view, that you find that the update is semi-conjugate. And above all, how do you specify the theta parameter that is the support of the uniform? And then I have a third question that is, I was a bit curious about the computation. You mentioned that your model and algorithm are scalable, right? Scalable with respect to sample size. So yeah. I gather that the computations are kind of quick because you are using marginal sampler. Is that correct?
Yes, okay, take the last one. We are using a marginal sampler. We're using like Neal's algorithm 8 or Neal's algorithm 3. And yes, computing, of course, the probability mass function for our shrinkage partition distribution is more involved than computing it for the CRP, which is very simple. It's just a gamma that we have to evaluate. So it's a little bit more involved, but the computation is very fast. We have a really nice low-level implementation in low-level language. It's very fast, and actually the bookkeeping you have to do is not that much, because you want to cache basically some counts in a contingency matrix. Our implementation is really fast, and also we found that evaluating the likelihood is far more expensive than evaluating the probability mass function. And so I found that's not really a deciding factor in the scalability of the algorithm. Yes, we are updating the shrinkage parameter. I mentioned that we're using a uniform prior, and that's a uniform 0 to theta. And Alessandra's asking, well, how do we pick that data? In fact, what we really do in the software is we allow you to have the prior on the shrinkage be a scaled beta distribution, where you can then specify the two parameters of the beta distribution. So you could put those equal to 1 and you get uniform, but you could also do anything else that you could do with a beta distribution. But then you still want to scale that by some amount. And we've just found that we want to scale that amount to be what seems reasonable according to our prior beliefs. And so we end up simulating partitions under our prior and see if the pairwise probability matches what we think and whatnot. We end up updating the omega parameters just with the slice sampler, and it's super fast and easy to do. So we haven't had any problems with that either.
I have a quick question, David.
Yeah.
Very interesting stuff. I was wondering, in either one of your dependent partition modeling frameworks, either the temporal type idea or the hierarchical, would it be possible to accommodate at different time points or in the hierarchical setting different pi i's? Would it be possible to accommodate those that have a different number of things that you're allocating? So is the number as you're thinking about as time increases, maybe not in the United States example because we have 50 states, but if you're thinking in others, maybe they're adding another element to be allocated or clustered in the partition. Is that possible to accommodate kind of a different n for each partitioning?
So that's a great question. That's actually something we're currently exploring, because you're right. Under the presentation I've given here, we need to be clustering the same items over time, or the same items in a hierarchical fashion. And so the number of items needs to be the same. We have done some preliminary thinking about how things might be able to adapt to, say, items coming in or coming out of the partitioning over time, but don't have anything very insightful to say about it right now. I think that's a great question.
Okay, we also have a question from Mario. Mario, please go ahead.
Yes, thank you. So I was wondering if there is a way to modify the prior to include like shrinkage parameters, not for any observation or any cluster, but basically for non-mutually disjoint subsets. So maybe like some expert thinks that two items should be together. So let's say A, B, C. So A should be together with B, but then there is also some probability that B is together with C, but nobody has ever thought that A and C should be together. But it might be like a posteriori, of course. But this doesn't fit into like a cluster specific shrinkage.
Yeah, that's a great question. For that, I would recommend using our Ewan's Pitman attraction distribution from that 2017 paper, where we could then have an n by n distance matrix, and then we could have the distance between, say, A and B be very small, the distance between B and C be very small, but then we maybe don't force the distance between A and C to also be small.
Okay.
Yeah, that's a fun idea too.
Okay, thank you.
Okay, let me see. Any other comments, questions for David? Maybe I can ask the last one. So, David, at the beginning you mentioned that with this data set you started like talking like maybe there are these 4 regions, but then you talk about divisions, and then inside the divisions you have states. So is there any way that you can adapt your method so you can put because you can put like, you can incorporate that information, like different baselines partitions that are kind of nested, and then for each partition you assign a different probability?
Yeah, that's a fun idea too, Felipe. So actually I would refer you to the discussion paper, or rather the LSP paper and the ensuing discussion, because people were thinking about how they could incorporate in the contributed discussions several different baseline partitions. And in the case you're talking about a hierarchical kind of framework where you have the regions and then the divisions and the individual states. But yeah, that's a fun idea that I think is still very much an open question of how to incorporate multiple baseline partitions.
Okay, thank you. So any other questions, comments? If not, well, let's thank David one more time for this.
Thank you very much for the invitation to speak. Thanks for coming.